Welcome. You have found a quiet place in the middle of your day, or perhaps the end of it. There is nothing here that needs your full attention. If you want to listen closely, everything that follows will give you something to hold on to. A story told slowly, built from real observations and real science, about one of the most studied and most distant objects we have ever turned our eyes toward. Tonight, or this evening, or whatever time it happens to be for you right now, we are going to spend some time with the Andromeda Galaxy. That name may already be familiar to you. You may have heard it in passing, in a documentary, in a classroom, in a conversation about space. Or you may be encountering it for the first time. Either way, there is no preparation required. The Andromeda Galaxy does not ask anything of you. It has been there for a very long time, and it will be there long after tonight. We will move through its story gently. We will talk about what it is, where it lives in space, how it came to be the way it is, and what astronomers have come to understand about it over many years of observation. There will be no rush. Each section will stand on its own. If you fall asleep somewhere along the way, that is entirely fine. If you drift back in and out, you will find the narration waiting for you. The Andromeda Galaxy is a large, calm, slowly turning structure of stars, gas, and ancient light. It is the most distant thing in the sky that a human eye can see without any equipment at all. And yet most people have never noticed it. That is one of the more interesting things about it. How something so vast can exist so quietly just above the horizon, unremarked, patient, enormous. Let us begin there. Let us begin with what it is. The Andromeda Galaxy is a galaxy. That word, galaxy, comes from the ancient Greek word for milk, a reference to the pale, cloudy band that crosses our own night sky and that ancient observers described as a river of milk or a path of light. Our own galaxy, the one we live inside, is called the Milky Way for the same reason. The Andromeda Galaxy is something like our galaxy, a vast, gravitationally bound collection of stars, gas, dust, and dark matter, but it is separate from us. It is its own enormous structure, located outside the boundaries of the Milky Way, existing in the space between galaxies. In terms of what kind of galaxy it is, Andromeda is classified as a spiral galaxy. Spiral galaxies have a distinctive shape, a bright central region, sometimes called the bulge or the nucleus, surrounded by flat, curving arms of stars and gas that wind outward like the arms of a slowly spinning pinwheel. From above, a spiral galaxy looks something like a whirlpool or a hurricane seen from space. From the side, it looks like a thin disk with a thicker center. The Andromeda Galaxy is believed to be viewed from Earth at an angle, slightly tilted toward us, so it appears as an elongated oval shape of soft light rather than a perfect circle. It is a large spiral galaxy by any measure. Estimates of its diameter vary depending on how the outer boundaries are defined, but Andromeda is generally considered to be slightly larger than the Milky Way in terms of its disk, though the two are comparable in total mass when dark matter is included. Some measurements suggest Andromeda spans roughly 220,000 light-years in diameter. Others place it somewhat smaller. The uncertainty here is not a failing of science. It reflects the genuine difficulty of measuring where a galaxy ends. Stars and gas become thick. At the center of the Andromeda Galaxy, as with most large galaxies, there is a supermassive black hole. The black hole at the center of Andromeda is estimated to be significantly larger than the one at the center of our own Milky Way. These are not the black holes of science fiction. They are not consuming stars constantly, and they are not dramatic sources of light. In their quiet state, supermassive black holes are simply extremely dense concentrations of mass around which everything in the galaxy, very distantly and very slowly, organizes itself. The Andromeda Galaxy contains hundreds of billions of stars. Some estimates suggest the number may be as high as 1 trillion. Most of these stars are invisible to us individually. They blend together into that soft oval glow. But they are there, each one a sun, many of them orbited by planets, some of those planets perhaps bearing conditions that could support life of one kind or another. We do not know. The distances involved make individual stars within Andromeda essentially unresolvable to current technology, except in specific cases. As a physical object in the universe, the Andromeda Galaxy is one of the largest and most massive structures in our immediate cosmic neighborhood. It is the dominant member of a small group of galaxies called the local group, which also includes our own Milky Way and dozens of smaller satellite galaxies. Andromeda and the Milky Way are the two largest galaxies in this group, and they exist in a relationship with each other that has been ongoing for billions of years. The Andromeda Galaxy takes its name from the constellation in which it appears, as seen from Earth. The constellation Andromeda is one of the 48 constellations listed by the ancient Greek astronomer Claudius Ptolemy in his 2nd century work, the Almagest. The constellation was named for Andromeda, a figure from Greek mythology, a princess, the daughter of the Ethiopian king Cepheus and Queen Cassiopeia, who appears in the legend of Perseus. The mythological Andromeda was chained to a rock by the sea as a sacrifice to a sea monster before being rescued by Perseus. Her story became embedded in the sky through the naming of the stars. The constellation Andromeda itself is a V-shaped or elongated arrangement of stars in the northern sky. It is connected to the constellation Pegasus by a shared star, and it sits in a region of sky that is reasonably well placed for northern hemisphere observers through autumn and into early winter. The galaxy that bears the constellation's name appears near the northwest corner of Andromeda, sitting faintly but visibly just to the side of the star New Andromedae. The object we now call the Andromeda Galaxy has been observed and recorded by human civilizations for a very long time. The earliest known written record of it appears in a star catalogue compiled by the Persian astronomer Abd al-Rahman al-Sufi, who worked in the 10th century. Al-Sufi described the object as a little cloud in his book of fixed stars, completed around 964 CE. His description is remarkably careful. He was noting something real, something he observed directly, and recording it for posterity. The phrase little cloud is one of the earliest surviving astronomical descriptions of what we now understand to be an entire galaxy. The object was also noted by later European astronomers. Simon Marius, a German astronomer, gave a detailed description of it in 1612 after observing it through one of the early telescopes. He compared its appearance to the light of a candle shining through horn, a description that captures the soft, diffuse quality of the galaxy's glow quite well. Despite his observation, Marius did not resolve the object into anything other than a nebulous patch of light. The technology of the time did not allow it. For a long time, the Andromeda Galaxy was known simply as the Andromeda Nebula. In early astronomical usage, the word nebula referred broadly to any fuzzy, diffuse patch of sky that did not resolve into individual stars. The nature of such objects, whether they were clouds of gas within our own galaxy, or whether they were entirely separate systems of stars at vast distances, was one of the central unresolved questions of astronomy into the 20th century. The matter was settled, or at least significantly advanced, by the American astronomer Edwin Hubble. Working at the Mount Wilson Observatory in California in the early 1920s, Hubble used the newly completed Hooker telescope, which was at the time the largest telescope in the world, to observe the Andromeda Nebula in detail. By identifying a specific class of variable stars called Cepheid variables within the nebula, he was able to estimate the distance to the object. His calculation showed that the Andromeda Nebula was far too distant to be located within our own galaxy. It was an entirely separate system of stars. This finding fundamentally changed human understanding of the scale of the universe. Our galaxy was not the whole of everything. The universe was vastly larger than previously understood. The Andromeda Nebula became the Andromeda Galaxy. The Andromeda Galaxy is approximately 2.537 million light-years from Earth. That distance is so large that it is difficult to hold in the mind in a meaningful way, but it is worth trying to approach it slowly. A light-year is the distance that light travels in 1 year. Light moves at roughly 300,000 kilometers per second, which means in 1 year it covers approximately 9.46 trillion kilometers. When we say that Andromeda is 2.537 million light-years away, we mean that the light currently reaching our eyes from that galaxy left its stars 2.537 million years ago. The light we see tonight departed Andromeda when our earliest human ancestors were just beginning to appear on the African continent. The galaxy as it exists right now, at this moment, is unknown to us. We are seeing its past. This is one of the quieter and more remarkable truths of astronomy. Everything we observe beyond our immediate neighborhood is historical. The farther away an object is, the further back in time we are looking. Andromeda is our nearest large galactic neighbor, and even it shows us a past that predates human civilization by an enormous margin. In terms of its position in space, Andromeda lies in the direction of the constellation Andromeda in the northern sky. Its celestial coordinates place it at a right ascension of approximately 0 hours 42 minutes and a declination of about positive 41 degrees, which means it sits fairly high in the sky for northern hemisphere observers. From locations above roughly 40 degrees north latitude, Andromeda is circumpolar for part of the year, meaning it never fully sets below the horizon. The galaxy is best positioned for observation during autumn evenings in the northern hemisphere, when it reaches its highest point in the sky around midnight in October and November. Despite its distance of over 2.5 million light-years, the Andromeda Galaxy is technically visible to the unaided human eye under sufficiently dark conditions. It appears as a soft, elongated smudge of light, dimmer than most stars, but perceptibly fuzzy rather than point-like. Under dark skies away from artificial light, observers with good eyesight can detect it easily once they know where to look. It is the most distant object regularly visible to the naked eye. Binoculars reveal it much more clearly, showing the elongated oval shape and the slightly brighter core. A small telescope begins to show hints of structure and the inner brightness gradient. The Andromeda Galaxy is the nearest large spiral galaxy to the Milky Way, but it is not the nearest galaxy overall. Several smaller, irregular satellite galaxies orbit both Andromeda and the Milky Way at closer distances. The large and small Magellanic Clouds, which are visible from the southern hemisphere as prominent patches in the sky, are satellite galaxies of the Milky Way located at distances of around 160,000 and 200,000 light-years respectively, far closer than Andromeda. But these are irregular, smaller systems. Among galaxies comparable in size and structure to the Milky Way, Andromeda is the nearest. Andromeda is also not stationary relative to the Milky Way. The two galaxies are moving toward each other. This is a fact worth sitting with for a moment. The vast distance between them is slowly, over geological and cosmic timescales, decreasing. The implications of this will be discussed later. For now, the important thing is simply that Andromeda has a location, a position in space, a relationship to us, and that position is in motion. The Andromeda Galaxy does not exist in isolation. It is part of a larger structure, a gravitationally bound collection of galaxies called the local group. The local group is the small cluster of galaxies to which both Andromeda and the Milky Way belong, and it spans a volume of space roughly 10 million light-years across. The local group contains more than 50 known galaxies, though most of them are small. The two largest and most massive members are the Andromeda Galaxy and the Milky Way. These two spiral giants are in some ways the anchors of the group. Most of the other members are gravitationally associated with one or the other of them as satellites. Andromeda's retinue of satellite galaxies is extensive. The two most notable are Messier 32 and Messier 110, both of which are visible through small telescopes in the same field of view as Andromeda itself. Messier 32 is a compact elliptical galaxy, a dense, rounded system of older stars with little gas or active star formation. Messier 110 is a larger, somewhat more diffuse elliptical. Beyond these two well-known companions, Andromeda is surrounded by a collection of smaller dwarf galaxies that orbit it at various distances, much as smaller moons might orbit a large planet. The full census of Andromeda's satellite galaxies is still being refined as astronomers survey the outer regions of the galaxy in greater detail. The Milky Way, for its part, has its own collection of satellite galaxies, including the Magellanic Clouds and a number of smaller dwarf systems. Some of these dwarfs are very faint and were only discovered in recent decades through detailed photographic surveys of the sky. The other large member of the local group is the Triangulum Galaxy, also known as Messier 33. This is a smaller spiral galaxy located roughly 3 million light-years away, close in space to the Andromeda Galaxy. It may be a satellite of Andromeda or simply a nearby companion. Its spiral arms are less tightly wound than Andromeda's, giving it a more open and looser appearance. Beyond the local group, the nearest significant collection of galaxies is the Virgo cluster, which lies roughly 50 to 60 million light-years away. The The local group itself is thought to be a peripheral member of an even larger structure called the Virgo supercluster, or Laniakea, which spans hundreds of millions of light-years and contains thousands of galaxies. The Andromeda Galaxy, enormous as it is a small part of this much larger cosmic web. Within the local group, Andromeda is gravitationally dominant alongside the Milky Way. The two large spirals shape the dynamics of the group. Their gravity influences the motions of the smaller members and ultimately determines the long-term fate of the entire collection. A spiral galaxy like Andromeda is not a simple object. It has distinct structural components, each with its own character, its own population of stars, its own history. At the very center of Andromeda is its nucleus, the dense, bright core of the galaxy. Hubble Space Telescope observations of Andromeda's nucleus revealed something unexpected and interesting. Rather than a single, centrally located peak of brightness, the nucleus of Andromeda appeared to have two distinct brightness peaks. For a time, this was puzzling. Eventually, astronomers concluded that this double nucleus was not actually two separate concentrations of stars. Instead, one of the apparent peaks is a cluster of stars that orbit the central black hole at a slightly different distance than the other, creating an off-center appearance due to the geometry of the orbit. This eccentric disk of stars creates the illusion of a second nucleus when viewed from our particular angle. The supermassive black hole at Andromeda's center is estimated to have a mass of approximately 100 million times the mass of the Sun, or roughly 100 million solar masses. For comparison, the supermassive black hole at the center of the Milky Way, known as Sagittarius A*, has a mass of about 4 million solar masses. Andromeda's central black hole is therefore substantially larger. Though it is currently in a quiet state, it is not actively accreting large amounts of material and is not producing the kind of high-energy jets seen in more active galactic nuclei. Surrounding the nucleus is the bulge, a large, roughly spherical region of older, redder stars. The bulge of a spiral galaxy is more densely packed than the disk and contains stars that formed earlier in the galaxy's history. These older stars have a different chemical composition than newer stars, reflecting the state of the universe at the time they were born. Less enriched with the heavier elements that form over time as stars live and die and seed space with their processed material. The bulge of Andromeda is quite prominent. It gives the galaxy its bright, concentrated center when viewed even with modest optical instruments. Extending outward from the bulge is the disk. The disk of Andromeda is where its spiral arms are located. The curving structures that contain younger stars, star-forming regions, dust lanes, and gas clouds. The spiral arms are not rigid structures. They are regions of higher density that move through the disk like a slow wave. Stars enter the arms, pass through regions of compression that can trigger new star formation, and then continue on their orbits beyond. The arms are marked by the blue light of young, hot stars and the reddish glow of ionized gas surrounding active stellar nurseries. Andromeda has several prominent dust lanes visible in photographs, dark, irregular streaks of absorbing material that cross the disk and indicate regions of dense gas and dust. These lanes trace the interstellar medium of the galaxy, the material between stars from which new generations of stars are eventually born. Beyond the disk, extending far out into space, is the stellar halo of Andromeda. This is a large, roughly spherical region surrounding the galaxy that contains older stars and globular clusters, ancient, densely packed spherical groups of stars that date back to the early universe. The halo of Andromeda has been extensively mapped in recent years and is surprisingly large. Studies using the Pan-Andromeda Archaeological Survey and other programs have found that the stellar halo of Andromeda extends to distances of several 100,000 light-years from the galaxy's center, and may even overlap at its edges with the outer halo of the Milky Way. Andromeda also possesses a large number of globular clusters, compact, spherical collections of hundreds of thousands to millions of stars that orbit the galaxy at various distances. The Milky Way has around 150 to 160 known globular clusters. Andromeda has been found to have over 500, making it one of the richer known globular cluster systems among nearby galaxies. These clusters are ancient, many of them formed more than 10 billion years ago, and they carry within them a record of the early history of their host galaxy. One of the most fundamental ways to understand a galaxy is to look at what kinds of stars it contains and where those stars are located. In Andromeda, as in the Milky Way, different regions are home to different stellar populations, and these populations tell a story about when and how the galaxy formed. Astronomers use a classification system that distinguishes between population 1 and population 2 stars, with some additional nuance. Population 1 stars are relatively young. They contain higher proportions of elements heavier than hydrogen and helium, which astronomers call metals regardless of their chemical nature. These younger stars formed from gas that had already been enriched by earlier generations of stars. The Sun is a population 1 star. Population 1 stars are found predominantly in the disk of a galaxy, particularly in and near the spiral arms. Population 2 stars are older. They contain lower proportions of heavy elements, reflecting their formation from the less enriched gas of the earlier universe. Population 2 stars are found in the bulge, the halo, and in globular clusters. Some of the oldest stars in Andromeda's globular clusters are among the most ancient objects known, with ages close to the age of the universe itself, around 12 to 13 billion years. The balance of these stellar populations in Andromeda tells us that the galaxy has a long history of star formation that has been occurring at varying rates over billions of years. The galaxy is not simply old. It has continued to form new stars, incorporate material, and renew itself over cosmic timescales. Evidence from resolved stellar populations in the outer disk and halo of Andromeda suggests episodes of significant star formation at various points in the galaxy's past, possibly triggered by interactions with other galaxies or mergers with smaller systems. The color of a galaxy, when measured carefully, reflects its stellar population. Galaxies dominated by old, cool stars tend to appear redder. Galaxies with active star formation and many young, hot stars appear bluer. Andromeda, when observed in different wavelengths, shows a gradient. Its center tends toward redder, older stars in the bulge, while its outer spiral arms show the blue tinge of more recent star formation. This is broadly consistent with what we see in other large spiral galaxies. In terms of raw numbers, the star count in Andromeda is genuinely difficult to pin down. Estimates have ranged widely, from several hundred billion up to around 1 trillion. The uncertainty arises partly from the difficulty of seeing and counting the faintest, smallest stars, which are the most numerous. Red dwarf stars, which are the most common stellar type in the universe, are very dim and contribute little to a galaxy's total light output, even though they make up the majority of its stellar population by number. The total mass of Andromeda's stars, when estimated from the galaxy's light output and dynamical behavior, is thought to be roughly 1 trillion solar masses, though again with significant uncertainty. A galaxy is not only stars. Between the stars lies the interstellar medium, a diffuse mixture of gas and dust that fills the space within the galaxy and serves as the raw material from which new stars eventually form. In Andromeda, the interstellar medium has been mapped at multiple wavelengths. Radio observations reveal the distribution of neutral hydrogen gas, hydrogen atoms that have not been ionized and that emit a specific radio frequency of 21 centimeters. This 21 centimeter emission has been used for decades to trace the structure of galaxies, including our own Milky Way and Andromeda. The neutral hydrogen in Andromeda extends well beyond the visible disk of the galaxy, stretching out into the outer reaches and providing a tracer of the galaxy's mass distribution at large radii. Infrared observations have mapped the dust content of Andromeda. Dust in galaxies is not simply dirt. It is a complex mixture of tiny solid particles composed of carbonaceous materials and silicates, formed in the outer layers of dying stars and distributed through the galaxy by stellar winds and supernova explosions. Dust absorbs ultraviolet and optical light from stars and re-emits it at infrared wavelengths, which is why galaxies often look different when observed in the infrared compared to the optical. The Spitzer Space Telescope, which was optimized for infrared observations, produced detailed maps of Andromeda's dust distribution that revealed ring-like structures in the disk. These ring structures in Andromeda's disk, concentrations of gas and star formation that appear as rings rather than continuous arms, have been the subject of considerable discussion. One hypothesis for their origin is that they were produced by a past collision or close interaction with one of Andromeda's satellite galaxies. When a smaller galaxy passes through or near the disk of a larger one, it can send waves of compression through the interstellar medium, triggering rings of enhanced star formation somewhat like the rings that spread across the surface of water when a stone is dropped into it. The star-forming regions of Andromeda are detectable by their emission of ultraviolet light from young, hot stars and by the ionized hydrogen, HII regions, that surround these young stellar nurseries. Surveys of HII regions in Andromeda have catalogued hundreds of these active sites, distributed through the disk and particularly concentrated in the inner ring structures. The rate at which Andromeda is currently forming new stars is somewhat lower than the star formation rate of the Milky Way. Our own galaxy is producing stars at a rate of a few solar masses per year. Andromeda's current star formation rate appears to be lower than this, suggesting it is in a somewhat quieter phase of its star-forming history. This is consistent with large, mature spiral galaxies, which tend to form stars at declining rates as their reservoirs of gas are gradually consumed. When astronomers measure the mass of a galaxy, they can do it in two ways. They can count the stars and estimate their mass from their brightness. Or they can measure how quickly the galaxy is rotating and use that to infer the gravitational mass needed to produce that rotation. These two methods do not agree. The rotational measurement consistently produces much higher mass estimates than the stellar count. The difference is attributed to dark matter. Dark matter is matter that does not interact with light. It emits no radiation, absorbs no radiation, and reflects no radiation. It is detectable only through its gravitational effects on ordinary matter and light. Its nature remains one of the most significant open questions in physics. We do not know what it is made of, but there is strong evidence that it exists because without it, galaxies would not rotate in the way they do, and large-scale structures in the universe would not have formed in the way we observe them. Andromeda, like the Milky Way and other large galaxies, is embedded in a massive halo of dark matter that extends far beyond the visible galaxy. The total mass of Andromeda, including its dark matter halo, is estimated at roughly 1 to 1.5 trillion solar masses, though estimates vary depending on the methods used and the assumptions made. The ratio of dark matter to ordinary matter in galaxies like Andromeda is approximately 5 to 1. For every kilogram of stars, gas, and dust, there are roughly 5 kilograms of dark matter. The dark matter halo of Andromeda is spherical or roughly spherical, unlike the flattened disk of the visible galaxy. It envelopes the entire structure and extends far out into the surrounding intergalactic space. The inner workings of this dark matter distribution, whether it is smooth or clumped, how dense it is at the center, how it influences the orbits of satellite galaxies, are active areas of research. The combined dark matter halos of Andromeda and the Milky Way likely overlap at their edges, which has implications for the dynamics of the local group as a whole. The gravitational pull of dark matter is what ultimately governs the motion of galaxies within the group and determines whether the group will eventually collapse together or expand outward with the general expansion of the universe. Understanding the dark matter content of Andromeda is not just an abstract exercise. It bears directly on calculations of how Andromeda and the Milky Way will interact in the future, since the dark matter halos of the two galaxies are already interacting gravitationally even as the visible portions of the galaxies remain separated by millions of light-years. The Andromeda Galaxy is moving toward the Milky Way. This is not a recent discovery, and it is not cause for alarm. The timescales involved are far beyond anything that would affect any living thing, any civilization, or any structure that exists today. But it is one of the more compelling facts about Andromeda, and it is worth describing carefully. Astronomers have measured the motion of Andromeda relative to the Milky Way using various techniques. The radial velocity, the component of motion directly toward or away from us, has been measured for decades from the Doppler shift of light from Andromeda stars. These measurements consistently show that Andromeda is approaching the Milky Way at a velocity of roughly 110 kilometers per second. That sounds fast, and in everyday terms it is roughly 400,000 kilometers per hour. But given the distance of 2.537 million light-years, this velocity means the collision, when it happens, is still billions of years away. The precise timing depends on the transverse component of Andromeda's motion, how much it is moving sideways relative to us in addition to directly toward us. This transverse component has been much harder to measure. Hubble Space Telescope observations conducted over several years managed to detect very slight positional shifts in the positions of stars in Andromeda, which were used to constrain this transverse velocity. The results suggested that Andromeda's path is aimed very nearly directly at the Milky Way, with only a modest sideways component. Based on these measurements, simulations predict that the first significant interaction between the two galaxies will begin in roughly 4 to 5 billion years. The word collision, while accurate in a technical sense, carries connotations that do not quite apply here. When two galaxies merge, it is not like two solid objects colliding. Galaxies are mostly empty space. The stars within them are so far apart relative to their sizes that two galaxies can pass through each other without a single star physically striking another. What does happen is gravitational disruption on a massive scale. The gravitational interactions between the billions of stars in both galaxies will pull stars out of their regular orbits, distort the shapes of both galaxies, and fling stars into new trajectories. Material from both galaxies will be stretched into long tidal streams. Satellite galaxies will be tossed into new orbits or expelled entirely. The likely outcome, as simulated by computer models using current measurements of both galaxies' masses and velocities, is that the two spiral galaxies will eventually merge into a single elliptical galaxy over a period of several billion years following their initial interaction. Elliptical galaxies are large, roughly oval-shaped collections of stars without the prominent disk and spiral arm structure of a spiral. This merged galaxy has sometimes been informally called Milkomeda or Milkdromeda. The name is not official, but it captures the idea. During the merger process, the interaction of gas clouds from both galaxies may trigger intense bursts of star formation. The compression of interstellar gas through galactic collision is one of the known mechanisms for triggering high star formation rates, and merging galaxies observed elsewhere in the universe often show elevated star formation. The Sun, if it still exists by the time the merger begins, and it may not, given that the Sun has a total lifespan of roughly 10 billion years and is currently about halfway through it, would have its orbit significantly altered. The probability of the Sun being ejected into the outer regions of the merged galaxy is non-trivial. But again, the physical survival of individual stars through such a merger is essentially guaranteed. The space between stars is simply too large for them to collide. This eventual merger is perhaps the most dramatic thing known about the future of Andromeda and our own galaxy. But it is worth keeping in mind that from the perspective of any beings who might exist billions of years hence, the merger would not be an event experienced on a human timescale. It would unfold across hundreds of millions of years, imperceptibly slow by any ordinary measure. The Andromeda Galaxy did not always look the way it does today. Like all galaxies, it has a history, a long sequence of formation, growth, disruption, and change that has unfolded over more than 10 billion years. The earliest phases of galaxy formation in the universe occurred in the first few billion years after the Big Bang. The universe at that time was filled with gas, primarily hydrogen and helium, along with dark matter. Under gravity, this material began to clump and collapse. Dark matter, which does not interact electromagnetically and could therefore collapse without the resistance of radiation pressure, formed the first large structures, vast halos of dark matter within which ordinary gas could then collect and cool. As the gas cooled and became denser, it began to form stars. These first generations of stars were short-lived and massive, burning through their fuel quickly and exploding as supernovae, seeding the surrounding gas with heavier elements. The galaxy we now call Andromeda formed through a process of hierarchical assembly, the gradual merging and aggregation of smaller systems into larger ones. The first building blocks were small proto-galactic fragments, which merged over time into larger structures. This process was not orderly or sequential. It involved multiple mergers happening at different times and from different directions, gradually building up the mass and the structure of the galaxy. The spiral disk of Andromeda formed as gas settled into a rotating disk, cooled, and began forming stars in that flattened configuration. The bulge and halo retained a record of the older, more chaotic early phases of assembly. Evidence for past mergers is written in the structure of Andromeda's halo. Detailed surveys of the stellar halo, particularly the Pan-Andromeda Archaeological Survey, which mapped the distribution of stars around Andromeda in great detail, revealed a complex network of stellar streams, shells, and overdensities. These are the remnants of smaller galaxies and star clusters that Andromeda has absorbed over its lifetime. When a smaller galaxy falls into a larger one, it is gradually pulled apart by tidal forces, and its stars are stretched into streams that curve around the larger galaxy's halo. These streams persist for billions of years, recording the history of past mergers. The most prominent of these stellar streams around Andromeda is called the Giant Stellar Stream or the Great Circle Tidal Stream. It is a coherent arc of stars extending far out from the main body of the galaxy, and it is thought to be the remnant of a significant merger event, possibly the infall of a relatively large galaxy that was disrupted and absorbed by Andromeda somewhere between 1 and 3 billion years ago. The shell structures visible in Andromeda's halo on the opposite side of the galaxy from this stream are consistent with the debris pattern expected from such a collision. The overall star formation history of Andromeda, reconstructed from the ages and compositions of its stellar population, suggests periods of elevated activity interspersed with calmer phases. There appears to have been a period of enhanced star formation several billion years ago, possibly associated with a merger event, followed by a more gradual decline to the present-day lower rate. The current structure of Andromeda, its disk, its arms, its ring-like features, its halo of stellar streams, is the accumulated result of billions of years of gravitational dynamics, mergers, gas accretion, star formation, and stellar evolution. It is, in a sense, a palimpsest, a record written and rewritten over cosmic time, with older layers still visible beneath the more recent ones if you know how to look. One of the things that makes modern astronomy so rich is that we can observe objects like the Andromeda Galaxy not only in visible light but across the full spectrum of electromagnetic radiation, radio waves, infrared light, ultraviolet light, X-rays, and gamma rays. Each wavelength reveals different physical processes and different components of the galaxy. In visible light, Andromeda shows its most familiar face: the elongated oval of soft glow, the bright central bulge, the dark dust lanes crossing the disk. This is the light primarily from stars. The majority of the galaxy's light output in the visible range comes from its stellar population, and the color and brightness distribution across the galaxy reflect which kinds of stars dominate in different regions. In ultraviolet light, Andromeda looks quite different. Ultraviolet emission is dominated by young, hot, massive stars, the recently formed stars that live fast and die young. Ultraviolet surveys of Andromeda therefore trace the distribution of active star formation across the disk. The spiral arm structures and ring-like features that contain star-forming regions appear prominently in ultraviolet images. In the infrared, dust becomes the main tracer. Warm dust heated by nearby stars emits infrared radiation, and infrared images of Andromeda reveal the intricate network of dust lanes and the ring structures in the disk with great clarity. The Spitzer Space Telescope produced some of the most detailed infrared maps of Andromeda, showing multiple concentric ring-like features and the complex distribution of heated dust. Radio observations, particularly at 21 centimeters, map the distribution of neutral hydrogen gas. Radio maps of Andromeda show the gas disk of the galaxy extending to much larger radii than the visible disk, and they reveal the detailed velocity structure of the rotating disk, each part of the galaxy moving at a slightly different speed as it orbits the galactic center, producing Doppler shifts that can be measured precisely. X-ray observations reveal the high-energy processes at work in the galaxy. X-ray telescopes have identified numerous point sources within Andromeda X-ray binaries, where a compact object such as a neutron star or black hole is pulling material from a companion star and heating it to extreme temperatures as it falls. The diffuse hot gas between stars also emits X-rays. The Chandra X-ray Observatory has produced detailed maps of the X-ray emission from Andromeda, cataloging hundreds of X-ray sources. The multi-wavelength view of Andromeda, taken together, provides a far more complete picture than any single observation. Astronomers use the combination of wavelengths to separate stellar populations, trace the life cycle of interstellar gas, identify sites of energetic processes, and build up a full accounting of the galaxy's mass, energy, and activity. Among the most scientifically valuable objects associated with the Andromeda Galaxy are its globular clusters. These dense, spherical collections of stars are among the oldest structures in the universe, and they offer a direct window into the early history of galaxy formation. A globular cluster is a tightly packed group of stars, typically containing anywhere from tens of thousands to several million stars, bound together by gravity and occupying a roughly spherical region of space. The stars within a globular cluster form together from the same cloud of gas, meaning they share a common age and roughly similar chemical composition. This makes globular clusters useful tools for stellar physics. By studying the stars within a cluster, astronomers can determine the age of the cluster with some precision by looking at which stars have evolved off the main sequence of stellar evolution. The globular clusters orbiting the Andromeda Galaxy have been catalogued and studied extensively. The current count of confirmed globular clusters associated with Andromeda exceeds 500, and candidate objects number in the hundreds more. This makes Andromeda's globular cluster system one of the richest known in the local group, significantly larger than the Milky Ways. The distribution of globular clusters around Andromeda is not entirely random. Some are concentrated in the inner regions and the bulge, while others orbit at very large distances in the outer halo. Some appear to be associated with the stellar streams in the halo, the remnants of disrupted dwarf galaxies, suggesting they were originally members of those smaller systems and were brought to their current locations as those systems were absorbed by Andromeda. Andromeda also hosts an unusual type of object sometimes called extended clusters or faint fuzzy clusters. Objects that share some properties with globular clusters but are larger, more diffuse, and less concentrated. These objects have no clear equivalent in the Milky Way system and represent an interesting puzzle in the study of star cluster formation. Some of the most ancient globular clusters in Andromeda have ages estimated at around 12 to 13 billion years, making them nearly as old as the universe itself. The chemical compositions of the stars in these ancient clusters record the conditions of the early universe. The relative abundances of elements reflect the nucleosynthesis history of the cosmos in its first few billion years. Studying these clusters is therefore not just galaxy archaeology. It is a way of probing the earliest phases of cosmic history. The Andromeda Galaxy is also known by its designation in the Messier catalog Messier 31, often abbreviated as M31. The Messier catalog is a famous list of astronomical objects compiled by the French astronomer Charles Messier in the 18th century. Messier was primarily a comet hunter, and he assembled his list as a practical reference, a catalog of objects that could be mistaken for comets but were not comets. He wanted to avoid repeatedly rediscovering the same fuzzy, non-cometary objects and confusing them with new comets he might find. The catalog was compiled between the 1750s and the 1780s and lists 110 objects. These objects include nebulae, star clusters, and what were then called nebulae but are now understood to be galaxies. The Andromeda Galaxy, as one of the brightest and most prominent fuzzy patches in the northern sky, was naturally included. Messier himself did not discover it. It had been known and recorded for centuries before his catalog. But his systematic listing gave it a widely used designation that persists in astronomical usage to this day. The Messier catalog is remarkable for what it inadvertently assembled. Without knowing the true nature of most of the objects it contains, Messier created a list that includes some of the most iconic and scientifically important objects in the sky: the Orion Nebula M42, the Pleiades star cluster, M45, the Crab Nebula, M1, a supernova remnant, the globular cluster Omega Centauri, and of course Andromeda, M31, along with its satellite galaxies Messier 32 and Messier 110. M31 sits at the very beginning of the section of the Messier catalog dealing with extended objects in the constellation Andromeda. Its companions M32 and M110 were added to the catalog separately and appear later in the numbering. Today, all three are recognized as part of the same galactic system. The designation M31 is commonly used alongside NGC 224, which is Andromeda's designation in the New General Catalogue, a later and more comprehensive catalogue of non-stellar objects compiled in the 19th century by John Lewis Emile Dreyer based on observations by William and John Herschel and others. Both designations refer to the same object, and both appear routinely in the scientific literature. Surrounding the Andromeda Galaxy is a diverse collection of smaller galaxies, dwarf galaxies that orbit Andromeda as satellites orbit a planet. These satellite galaxies range in brightness from objects visible in small telescopes to extremely faint systems detectable only in deep photographic surveys. The two most prominent satellite galaxies are Messier 32 and Messier 110, both of which appear in the same telescopic field of view as Andromeda itself. Messier 32 is a compact elliptical galaxy, a dense, rounded system notable for its unusually high surface brightness. Compact elliptical galaxies like M32 are relatively rare, and M32 itself is thought to be a stripped former spiral or elliptical galaxy that was once larger but lost much of its outer material to tidal stripping as it orbited Andromeda over billions of years. This stripping has left it as a dense, compact remnant. Messier 110 is a larger, more diffuse elliptical galaxy. It contains a population of globular clusters and shows some evidence of internal dust and gas, which is unusual for an elliptical galaxy. It orbits Andromeda at a greater distance than M32 and appears to have had a quieter history of interaction. Beyond these two well-known companions, the census of Andromeda's satellite system has grown considerably with modern surveys. Dwarf spheroidal galaxies, very faint, low-surface brightness systems with few stars, have been found at various distances around Andromeda. These include systems like Andromeda I through Andromeda XXXV and beyond, reflecting the ongoing discovery of fainter and fainter companions. Some of these dwarfs are so faint that they were only found by searching for overdensities of resolved stars in deep photographic surveys. The spatial distribution of Andromeda's satellite galaxies has attracted attention. A study published in 2013 noted that a significant fraction of the satellites appeared to be arranged in a large, thin plane, a flattened disk-like arrangement rather than a random three-dimensional distribution. This was unexpected, because standard cosmological models predict that satellite galaxies should be distributed more isotropically around their host. A similar planar arrangement of satellites was noted around the Milky Way. The interpretation of this observation has been debated. Some argue it reflects particular pathways by which satellites were accreted, while others see it as a genuine challenge to models of galaxy formation. The matter has not been fully resolved. The satellite galaxies of Andromeda interact with it gravitationally. As they orbit, tidal forces from Andromeda can stretch and distort them, pulling stars out of their outer regions into the extended halo. Some of Andromeda's stellar halo features, the streams, shells, and overdensities visible in deep surveys, may be the debris of former satellites that have been partially or completely disrupted over billions of years. The Andromeda Galaxy occupies a central position in the history of astronomy. Several of the most significant conceptual advances in our understanding of the universe were directly tied to observations of Andromeda. The most transformative of these was Edwin Hubble's determination in the early 1920s that Andromeda lay beyond the Milky Way, that it was a separate island universe of stars, entirely distinct from our own galaxy. Before Hubble's work, the scale of the universe was genuinely uncertain. The debate over whether objects like Andromeda were nearby clouds of gas or distant collections of stars was sometimes called the Great Debate, and it was resolved not by argument but by observation. Hubble's identification of Cepheid variable stars in Andromeda, stars whose pulsation periods are directly related to their intrinsic brightness, allowing their distances to be calculated, gave a quantitative distance that placed Andromeda far outside any reasonable estimate of the size of our own galaxy. This discovery had enormous consequences. It demonstrated that the observable universe was vastly larger than previously appreciated, that the Milky Way was not the universe but merely one galaxy among many. It opened the door to the modern understanding of the cosmos as a vast collection of galaxies, each containing billions of stars. Subsequent work on Andromeda contributed to other foundational developments. The rotation curve of Andromeda, the variation of orbital speed with distance from the center, was among the early observations that pointed to the existence of dark matter. Vera Rubin and W. Kent Ford measured the rotation curve of Andromeda in the early 1970s and found that stars in the outer disk of the galaxy were moving faster than expected based on the mass of visible matter alone. This flat rotation curve was difficult to explain without invoking additional, unseen mass, the signature of a dark matter halo. Similar flat rotation curves were subsequently found in many other galaxies, cementing the case for dark matter as a ubiquitous component of galactic structure. More recently, detailed studies of Andromeda's stellar halo using resolved stellar populations, mapping individual stars across the enormous extent of the halo, have contributed significantly to understanding the processes of galaxy growth through merger and accretion. The Pan-Andromeda Archaeological Survey and similar projects have revealed the full complexity of Andromeda's outer structure and have provided benchmarks for testing theories of hierarchical galaxy formation. Andromeda continues to be a primary target for observational programs across virtually all wavelengths. Its proximity, making it the only large spiral galaxy whose individual stars can be resolved with current technology, makes it irreplaceable as a laboratory for galaxy science. What we learn from Andromeda informs our understanding of spiral galaxies throughout the universe. For an observer with interest in actually seeing the Andromeda Galaxy, the experience varies considerably depending on equipment and conditions. With the naked eye under dark skies, Andromeda appears as a faint, elongated smudge, a soft oval of light noticeably larger than a star and distinctly non-stellar in character. Its total brightness, when measured, corresponds to an apparent magnitude of approximately 3.4, which is in principle visible even under moderately good conditions. However, its light is spread over a large area of sky rather than concentrated in a point, which makes it harder to detect than a star of the same total brightness. The central region is brighter and more readily visible. The outer parts of the disk fade gradually into the background sky. Finding Andromeda with the naked eye requires knowing where to look. The most common method uses the Great Square of Pegasus, a prominent, easily identified square of 4 stars visible in the northern autumn sky, as a starting point. From the Great Square, one traces a line through the stars Myric and then Mu Andromedae, and the galaxy lies nearby. Once you know the location and know what you are looking for, it becomes much more findable. Binoculars improve the view substantially. A typical pair of binoculars will show the central bulge of Andromeda clearly and begin to show the elongation of the disk. The 2 companion galaxies M32 and M110 may be visible as additional faint smudges nearby. The overall impression is of a diffuse, somewhat oval patch of light with a brighter center, not spectacular by the standard of color astrophotographs, but genuine in a way that photographs cannot fully convey. When you observe Andromeda with binoculars, you are seeing light that has traveled for over 2 million years. A small telescope, perhaps 70 to 100 millimeters of aperture, will show more of the disk and may begin to reveal hints of the dust lanes that cross the inner disk. The companion galaxies become more distinct. At medium magnification, the core of Andromeda shows as a noticeably brighter, almost star-like nucleus surrounded by a halo of softer glow. Astrophotography of Andromeda has become accessible to amateur astronomers with modest equipment. Even a camera on a simple tracking mount can capture the basic structure of the galaxy, the disk, the central bulge, and the beginnings of the dust lane structure in a relatively short exposure. Long exposures from dark sites can reveal the outer disk and even hints of the faint, extended halo. Amateur images of Andromeda have in recent years reached impressive depths, and some have been combined into mosaics showing the full extent of the galaxy and some of its surrounding features. Professional imagery of Andromeda, from the Hubble Space Telescope, Spitzer, Chandra, and other observatories, has produced stunning results that reveal the galaxy in fine detail at specific wavelengths. The Hubble image of Andromeda released in 2015 which covered a portion of the galaxy at extremely high resolution and was made up of many individual pointings, resolved hundreds of millions of individual stars within the galaxy and required months of observing time to assemble. It remains one of the largest and most detailed images of any external galaxy ever taken. The Andromeda Galaxy exists within the flow of cosmic time in ways that are worth contemplating quietly. It has a past that extends nearly to the beginning of the universe, and it has a future that will unfold over timescales that dwarf all of recorded human history. When the universe was very young, in its first few 100 million years, the structures that would become galaxies were only beginning to coalesce from the expanding plasma of the Big Bang. The dark matter halos that would eventually attract and hold the baryonic matter of stars and gas were forming through gravitational collapse. The proto-galactic fragments that would eventually merge and build Andromeda were scattered across what would become a small region of the observable universe. The first stars in Andromeda, by most estimates, formed somewhere between 12 and 13 billion years ago. These stars, embedded in the oldest globular clusters and the inner bulge of the galaxy, are relics of that earliest epoch of galaxy building. They contain very little of the elements heavier than helium, elements that had to be manufactured by stars and distributed into the interstellar medium over billions of years of stellar evolution. Their low metallicity is a direct record of the chemical state of the universe at the time they formed. As billions of years passed, Andromeda grew through a combination of internal star formation and the accretion of smaller systems. The spiral structure developed as the disk settled and stabilized. The rich halo of stellar streams accumulated as satellites were disrupted and absorbed. The galaxy's mass gradually increased. At the present moment, which, it is worth remembering, is actually 2.537 million years in Andromeda's past from our perspective, the galaxy appears to be in a relatively mature, somewhat quiescent state. It is forming stars, but at a lower rate than in its youth. Its spiral arms are present but not dramatically active. Its core is quiet. Looking forward, Andromeda will continue on this general trajectory for roughly 4 to 5 billion years before the interaction with the Milky Way begins in earnest. The merger process, once underway, will likely take another few billion years to complete. The resulting elliptical galaxy will then evolve slowly, its star formation declining further as its gas is consumed or ejected, and it will gradually become redder and more quiescent as its stellar populations age. Over tens of billions of years, the fused galaxy will settle into a slow decline, with fewer and fewer new stars being born as the raw material becomes increasingly scarce. On the largest timescales, beyond what any current model can reliably predict, the merged galaxy will exist within an increasingly empty universe as the expansion of space carries other galactic groups beyond the reach of communication or observation. The local group, held together by its own gravity, will remain intact long after the broader universe has become inaccessible. But even the local group will eventually exhaust its capacity for renewal. These are the quiet facts of deep time. They require no urgency. They are simply the nature of things on the longest scales we know how to describe. The Andromeda Galaxy occupies an interesting position in the broader culture of science communication. It is close enough to be visible with the naked eye, which gives it an immediacy that more distant deep-sky objects cannot offer. And it carries a story, the forthcoming merger with the Milky Way, that is dramatic enough to capture attention while being scientifically grounded enough to be discussed accurately. The forthcoming galactic merger between Andromeda and the Milky Way has appeared in popular science writing, documentaries, and educational media many times. It is frequently presented as a dramatic event, and in a sense it is on the appropriate timescale. But the way it is sometimes communicated can create misleading impressions. Words like collision and crash suggest an immediacy and a violence that does not reflect what will actually occur. The merger will be a slow, gravitational dance lasting hundreds of millions of years, essentially invisible on any human timescale, and posing no direct physical threat to individual stars or planetary systems. Andromeda has also appeared in science fiction, often as a setting for stories set in the far future when humans might have developed means of traveling between galaxies. It represents, in a narrative sense, an ultimate destination, the nearest large galaxy, still impossibly far away by current human capabilities, but close enough in cosmic terms to be plausible as a long-term goal. This fictional treatment of Andromeda reflects something real about how distant objects capture the imagination. To understand the Andromeda Galaxy more fully, it is useful to place it in the context of other galaxies, to compare and contrast it with systems that share some features and differ in others. The Milky Way is the most natural comparison. Both are large barred spiral galaxies, though the barred structure is more evident in the Milky Way than in Andromeda. Both contain hundreds of billions of stars. Both have extensive dark matter halos, large populations of globular clusters, and satellite systems of smaller galaxies. The two are close enough in mass and size to be considered near twins, though precise comparisons remain uncertain because measuring our own galaxy is in some ways harder than measuring a galaxy we can observe from outside. The Triangulum galaxy Messier 33 is the third large galaxy in the local group. It is smaller than both Andromeda and the Milky Way, a somewhat open, loosely wound spiral with more active star formation relative to its mass. Triangulum is close enough to Andromeda that the two may have interacted in the past, and simulations suggest that Triangulum may eventually participate in the Andromeda-Milky Way merger. Beyond the local group, the Virgo cluster contains thousands of galaxies of various types, including large ellipticals and spirals. The giant elliptical galaxy M87 in Virgo, famous as the host of the first supermassive black hole to be directly imaged by the Event Horizon Telescope, provides a useful contrast with Andromeda. M87 is vastly more massive, has a much more active nucleus, and contains no spiral structure. It represents a different stage and type of galactic evolution, the kind of massive elliptical that results from many galactic mergers over cosmic time. Andromeda itself may be compared to other large spirals observed in the wider universe. Galaxies like NGC 253, NGC 1232, and countless others seen at various distances and inclinations. These comparisons help establish how typical or atypical Andromeda is, and what it tells us about spiral galaxy formation and evolution more generally. By most measures, Andromeda is a relatively ordinary large spiral, which is itself an interesting conclusion. The nearest large spiral galaxy to us is, in most respects, a fairly representative example of what large spiral galaxies are like. The Pinwheel Galaxy M101, the Whirlpool Galaxy M51, and the Sombrero Galaxy M104 are all spiral galaxies visible in small telescopes and much studied, but each presents from a different angle and with different structural features than Andromeda. M51 in particular is famous for its ongoing interaction with a smaller companion galaxy, an active version of the kind of merger that Andromeda and the Milky Way will one day undergo. The Andromeda Galaxy does not exist in isolation from the broader universe. It participates in the flows and cycles of matter, energy, and structure that characterize the cosmos on large scales. Galaxies like Andromeda are the factories of the universe, the sites where most of the ordinary matter in the cosmos is assembled into stars, processed through stellar evolution, and redistributed as gas enriched with the products of nuclear burning. The heavy elements that make up rocky planets, biological molecules, and all the chemical diversity of the observable universe were largely forged in stars within galaxies and then returned to the interstellar medium through stellar winds and supernovae. Andromeda, with its hundreds of billions of stars and its long history of star formation, has participated in this elemental manufacturing on an enormous scale. The matter that flows through a galaxy like Andromeda does not stay there permanently. Supernova explosions and the collective winds of massive stars can drive material out of the disk and into the halo and eventually into the intergalactic medium, the sparse gas that fills the space between galaxies. This outflowing material carries with it heavy elements produced in stellar interiors. At the same time, galaxies can accrete fresh material from the intergalactic medium, cool gas that falls inward under gravity and eventually joins the disk, providing new fuel for star formation. This cycle of accretion and outflow is one of the key processes regulating the star formation rates of galaxies over time. As galaxies consume their gas in star formation and lose some material through outflows, their star formation rates decline. Andromeda's current relatively low star formation rate may reflect this long-term consumption of its gas supply. The hot gas in the halos of large galaxies, observable in X-rays, is another component of this cycle. Large galaxies like Andromeda are surrounded by extended atmospheres of hot, diffuse gas that were heated by supernovae and gravitational infall. This hot halo represents a reservoir of material that can cool and eventually contribute to star formation on very long timescales. It also interacts with the satellite galaxies that orbit through it, stripping their gas and affecting their own ability to form stars. On still larger scales, galaxies like Andromeda are nodes in the cosmic web, the vast filamentary network of dark matter and gas that organizes the large-scale structure of the universe. Galaxies tend to be located at the intersections of these filaments, fed by material flowing along them. The local group of which Andromeda is a member occupies a relatively underdense region of the universe between the Virgo supercluster and other large structures. The dynamics of the local group and the evolution of its member galaxies are in part a product of this large-scale environment. Andromeda is a patient thing. It turns at a rate imperceptible to any single lifetime. Its arms wind outward at velocities that seem fast in absolute terms, hundreds of kilometers per second, but that cover distances so vast that 1,000,000 years might pass before any visible change accumulated in the pattern we observe. The stars within Andromeda orbit the galactic center over periods of hundreds of millions of years. A star like the Sun, if it were located in Andromeda rather than the Milky Way, would take roughly 200 to 250 million years to complete one orbit around the galactic center. In the estimated 10 to 12 billion years of its history, Andromeda has turned on its axis perhaps 40 to 50 times. That is not many revolutions. A coin spun on a table completes more revolutions in a minute. The dust lanes crossing Andromeda's disk are structures that will persist for billions of years before the material within them is transformed into stars or otherwise dispersed. The globular clusters orbiting at great distances from the center will continue their orbits long after the Sun has exhausted its fuel and the Earth has been absorbed into the expanded solar remnant. These ancient star clusters are, in a sense, the most durable things associated with the Andromeda Galaxy, compact enough to resist disruption, old enough to have survived most of the galaxy's history. The soft light that reaches our telescopes and eyes tonight from Andromeda left that galaxy when the genus Homo had barely emerged on the plains of Africa. Our ancestors were not yet anatomically modern humans. The biological and cultural changes that would eventually lead to cities, writing, science, telescopes, and the ability to measure the distance to that light source were all still in the future by geological timescales. And yet there the light was crossing the void, covering 9 trillion kilometers per year for 2.537 million years, arriving at a small rocky planet and entering the instruments of observers who had developed the curiosity and the tools to ask where it had come from and what it meant. That is a quiet kind of connection, not dramatic, not urgent, simply the arrival of old light from a familiar neighbor, enormous, turning slowly, full of stars. The Andromeda Galaxy has been studied by virtually every major astronomical observatory and space mission of the modern era. It is one of the most intensively observed objects in the sky, and the body of data accumulated about it is vast. The Hubble Space Telescope has been particularly important in the study of Andromeda. Its ability to resolve individual stars within the galaxy, something essentially impossible from the ground, has enabled studies of stellar populations, the identification of Cepheid variables for distance measurement, the mapping of the stellar halo, and the characterization of the galaxy's nucleus. The Hubble archive contains many thousands of observations of Andromeda accumulated over decades of operation. The Spitzer Space Telescope, operational from 2003 to 2020, conducted extensive infrared observations of Andromeda that revealed the distribution of warm dust in the disk and the structure of the ring features. Spitzer's images showed Andromeda in a warm, brownish-red palette very different from the silver-blue optical images, tracing the dust lanes and heated interstellar medium with great clarity. The Chandra X-ray Observatory has cataloged the X-ray point source population of Andromeda, the X-ray binaries, supernova remnants, and other energetic objects within the galaxy, and has mapped the diffuse X-ray emission from hot gas in the inner galaxy and halo. Radio observations, particularly from the Very Large Array and other radio telescopes, have mapped the neutral hydrogen gas in Andromeda with high resolution, revealing the velocity structure of the gas disk and the extent of the gas beyond the visible disk. The European Space Agency's Herschel Space Observatory, which operated at far-infrared and submillimeter wavelengths, provided additional views of the cold dust and gas in Andromeda's disk, complementing Spitzer's warmer dust maps. Ground-based observatories have also contributed enormously. The Pan-Andromeda Archaeological Survey, conducted using the Canada-France-Hawaii telescope, is one of the most ambitious ground-based programs targeting Andromeda. It mapped the stellar population of Andromeda's halo over a vast area, revealing the complex network of stellar streams and the enormous spatial extent of the galaxy's outer structure. This survey was a landmark in the study of galactic halos and hierarchical galaxy formation. The forthcoming Nancy Grace Roman Space Telescope, sometimes called the Hubble successor, is expected to conduct wide-field surveys that will be ideally suited to studying Andromeda's extended halo and satellite system with unprecedented depth and area coverage. There is a particular experience of standing outside on a clear autumn night in the northern hemisphere and knowing where Andromeda is in the sky. Knowing that the faint smudge between two stars in the northeastern sky is not a cloud, not a smear on the eye, but 2.5 million light-years of space away. The galaxy sits there, whether or not anyone is looking. It has been visible in the night sky for as long as there has been a night sky with an Earth to observe it from. Countless generations of humans lay on their backs under the stars and did not know what that faint oval of light was. They named the stars around it, told stories about the mythological princess after whom the constellation is named, and simply accepted the fuzzy patch as one more feature of the sky, unremarkable precisely because they lacked the framework to understand its scale. Now we have that framework. We know that each point of light in the sky is a sun. We know that some of those points are not individual stars but entire galaxies containing hundreds of billions of suns. We know that the faint oval near the star Mirror is one of those galaxies, our nearest large neighbor, a structure of comparable scale to the one we live inside. That knowledge does not necessarily make the view more beautiful. It makes it different. There is a quiet satisfaction in looking at a familiar part of the sky and understanding what you are actually seeing. Not a nearby cloud of gas but a galaxy, turned slightly toward us, sending light that predates humanity. The Andromeda Galaxy is the same whether observed with a naked eye, binoculars, a small telescope, or the Hubble Space Telescope. It does not change based on how much we know about it. It simply is turning slowly, forming a few stars per year, orbited by its satellites, approaching us at 110 kilometers per second, carrying within it the light and mass of hundreds of billions of suns. It is one of the calmer facts of the universe. It does not demand attention. It does not announce itself. It simply hangs in the northern sky, soft and oval and ancient, available to anyone who knows where to look and who takes a moment to look. As we near the end of this long, slow exploration of the Andromeda Galaxy, it seems right to let the pace soften a little further. No new information is necessary at this point. The picture is complete enough. What remains is simply to sit with what has been described. The Andromeda Galaxy is a galaxy, a spiral, It lies 2.537 million light-years away, visible to the naked eye on dark nights as a soft patch of light in the constellation Andromeda. It contains hundreds of billions of stars, at least one supermassive black hole, a rich system of globular clusters, a complex halo of stellar streams, and a large population of satellite galaxies. It is approaching us slowly. It has been turning for billions of years. It will continue turning for billions more. Its name comes from ancient mythology, but the object itself is older than any story we have told about it. The light leaving Andromeda tonight will arrive at our planet in 2.537 million years. We will not be here to receive it in any meaningful sense, but the light will come regardless. There is something restful about objects on this scale. They are indifferent to urgency. They do not hurry. The Andromeda Galaxy has spent more than 10 billion years becoming what it is, and it will spend billions more years slowly changing into something else. All of that happens at a pace that has nothing to do with the speed of any human concern. If you are still awake, thank you for spending this time with a galaxy. If you are drifting, that is entirely fine. The Andromeda Galaxy will still be where it was when you open your eyes. Still turning, still approaching, still old. The stars in Andromeda do not know they are being observed. The galaxy has no awareness of the small planet from which humans have spent the last few centuries learning to understand it. It simply exists, in its vast and quiet way, in the darkness between here and there. That is enough. That is more than enough. Rest well. The sky is still there, and Andromeda is in it.